This is my sixth video on how to prepare for the Cambridge interview, concentrating on the natural science physical. We still have the two problems from 200 puzzling physics problems with hints, and today I have two problems. Both of them has two asterisks, meaning them they are actually very hard to think from the first step. But well, if you know what is the true fundamental method of it, it will be very clear. So let's start from problem 105. There's a heavy flexible inelastic chain of length L placed almost symmetrically onto a light pulley, which can rotate about a fixed axle, as shown in the figure. And what will the speed of the chain be when it leaves the pulley? So you might first imagine that, oh, it will leave like this with the velocity. But if it's so trivial, would this be an interview problem? No. So let's think about what will happen if the velocity of the chain is very big. It might be something when you can find here. The velocity is very big, and then this part will go up, and it becomes something like this, While the this part is still closely attached, but not attached. Just they are at the same plane. But the left part has flight, So we're going to figure out when and why it will do something like this, okay? And okay, to address the problem, we first have a little theorem. That is, when a chain moving at a uniform speed along a closed curve of arbitrary shape continues moving, and we can find of this equation the eternal tangent of it, F equals to rho. This is the linear density of it times v squared. This is very similar to the one you've learned in A-level physics when we calculate the wave speed of the wave on a tangent chain, right? So let's use some induction to prove it. So consider the chain moving with a speed of v. The force stretching the chain has to be the same magnitude F everywhere, as the tangential acceleration of its length is zero. So it can be any shape, and we just focus on this tiny part here. Let's assume that it undergoes a circular motion with a radius r. Then the mass of this piece of length is delta gamma. The mass would be alpha r times rho times delta gamma, right? The acceleration of it is tangential. Perpendicular is v squared over r. So it has something like this. The left part is F, right part F, and it contributes to an overall centripetal force, right? So we have known that for this kind of question, the magnitude of the centripetal force is F times sine 2 sine delta gamma over 2. This, when delta gamma is very small, it equals to alpha F times delta gamma. So now we have F times delta gamma equals to this delta M times a perpendicular. We have something of this, right? This leads to a relation of F equals to rho times V squared. So you can see that it does not depend on the radius. So it is actually correct to any of the chain which is flexible and moving at a uniform speed. This uniform speed can be instantaneous, so it is also useful in this problem. And another thing that is, this chain must not be in contact with any other body, because we want the sum of the external force to be zero. And just like what I've said, it should be noted that this result is independent on the radius of the curvature, r of the arc form. And it also applies to chains or ropes moving a straight line, right? Because r can be formally taken as infinity. In the present case, the chain becomes detached from the pulley as a result of its accelerating motion when the freedom condition is satisfied. So, when the internal tension of it becomes rho times v squared, now it is not in contact with any other body, so it is detached. I guess you have heard, and if not, you can just review it. Let's denote the displacement of the chain by x, okay, and the acceleration of the right hand side by a. We can draw something like this. This is x, this is a. We will assume the internal tension of the chain by F. So we have this. This is for the left part, and for the right part, we also have that. Now you have already set up equations about F, A, and X, right? So now we are going to calculate the velocity from the conservation of energy. The lost the kinetic energy comes from the lost gravitational potential energy, right? So the mass of the whole chain is this, and we use it to times 1/2 times v squared. It equals to the decrease in potential energy, and we can assume that this part decreases by height x. So the gravity force is rho xg, and the height decreased is x. Sure. We set up this, and we find when F equals to rho v squared, we find x equals to L over 2 times square root of 2, and v equals to this. So if you just, use something like, oh, it would just be something like this, it will have a result of this, and it's clearly not a right answer. And you can also find it in the real life, that it will never become something like this. You must know that left part of it will go upwards because the force is too big, right? Okay, and that's all for this question. I'll move this upwards. Sure. Okay, and next we have the problem of 108. This is also a very hard problem. A fire hose of mass m and length l is coiled into a row of radius r. R can be neglected if we are considering L. The hose is sent rolling across level ground with initial speed v sub 0, while the free end of the hose is held at a fixed point on the ground. The hose unrolls and becomes straight. So how much time does it take for the hose to completely unroll? Second part, the speed of the roll continually increases and its acceleration a is clearly a vector pointing in the same direction as its velocity. On the other hand, the vector resultant of the horizontal external forces, the frictional force plus the restraining force at the fixed end of the hose points in the opposite direction. So how are these two facts consistent with Newton's second law? To simplify the analysis, suppose the initial kinetic energy of the roll to be much higher than its potential energy, thus allowing the effect of gravity to be neglected. Assume further that the hose can be considered as arbitrarily flexible and the work necessary for its deformation, air resistance, and rolling resistance can all be neglected. So, first we will determine the speed of the roll as a function of the distance it has covered. The mass of the moving part, the right part, will denote here, this is x, and we want to find its velocity. So the right hand side m would be some partial of it, and Vx we can find it by this. This is the initial speed, initial kinetic energy, plus this is the initial angular energy. This is because it does not have the center of mass moving at a velocity of v. It is also spinning around its symmetrical line. The thing into the paper. So apart from its kinetic energy, along with the motion of the center of mass, it also have an angular motion energy. You can't neglect that. It also contributes to a large part, and because it is not the arc, the whole circle is made of the rope, so the the I of it is 1/2 times m r squared. You can't neglect this coefficient, right? If it equals to the kinetic energy of nowadays, and you just write this down, right? This r and the l, you have to find that out. So we can actually know that the Vx equals to this. This is very easy. So when x increases, the velocity increases, and we calculate for the time t. It is actually this, right? You just walk by little displacement, and you can find by integration it is like this. So the time taken to unroll is obviously shorter than if the hose has unrolled with uniform velocity, right? So the system, and next we'll consider about the second part of the question. It really seems a little bit, just confusing, but the system consisting of a roll of decreasing mass and increasing speed. So does the total momentum really leads to really has the direction of rightwards? No, maybe not. So it cannot be considered as a pointed mass. The according to the Newton's second law, it will be something like the sum of F external equals to the derivative of momentum of total momentum, right? So P the momentum equals to M times V, right? And clearly as x increases, px decreases. This means the mass of the piece of motion decreases faster than the rate at which its speed increases. The direction of the resultant force acting on a system we can calculate is the derivative of momentum. It is actually leftwards, so there's nothing wrong about our calculation and nothing wrong about the Newton's second law. When these two disobeys, you just need to question yourself, because Newton's second law will never be wrong in such a circumstance, and maybe you just need to find out something else. And I will provide 3 or something like 2 hints for you when you encounter such problems. The first one is, so does it be in contact with other objects? I mean, so have you considered all the external thing? I mean, sometimes there's a field, electric field, magnetic field, and it can contribute to the energy, right? There's something more like air resistance, or in this problem, they have friction and the leftwards F. And the second one, you should ask about yourself. Have I do it in a right reference frame? If you do this problem in the center of mass frame, you may find it very hard. And also in the center of mass reference frame, the Newton's second law sometimes need to be adjusted because of the it is not a constant velocity. It has some acceleration, and you have to add up for the inertial force, which is F equals to minus ma, and this is the some consumption you have to be made. So consider about these 2 things, and I hope all of your physics preparation has been done very well, and I will keep uploading new videos about this. So meet me next time, and I am Alex, and happy to hear from you next time. So farewell.